Now, chapter number 6, electromagnetic induction. So, see, previously we already discussed this thing. Initially, the branches electricity and magnetism were developed separately. But then after, in the previous chapters, we discussed this thing. The experimental observations by Ørsted, Faraday, represents this thing. Electricity and magnetism are inseparable, and these two are associated with each other. Okay, and in previous chapter we discussed this thing. The moving charges means the electric current produces the magnetic field. Now scientists thought like this: if electric current means the moving charges produces the magnetic field, then opposite is possible or not. It implies that whether the changing magnetic field or moving magnet can produce the electric current or EMF. So in that particular direction, so many scientists worked, but then after, finally, scientists Faraday and Henry were succeeded to represent this thing experimentally, the moving magnet or changing magnetic field that produces the electric current, or we can say EMF. So let's discuss different experiments which were performed by this scientist, and with the help of those experiments, this thing was established, the moving magnetic field or changing magnetic field that produces the EMF or electric current. Okay, now see, suppose first we think about this experiment number 1. Now the experiment was performed like this. This one is the coil connected with the galvanometer, and against it the bar magnet was placed as shown in the figure in such a way that the north pole of the bar magnet is facing to the coil. In that way, as shown in the figure, the arrangement was made. Now we know this thing, if magnet is there, definitely in the surrounding of it, magnetic field will be there. Now, these magnetic field lines will pass through this particular coil also. But he observed this thing, in this particular situation, galvanometer is not showing the deflection. When galvanometer is not showing the deflection, it implies that there is no current in this particular loop. Okay, there is no current in this particular loop. But as soon as the magnet was moved, he observed this thing, galvanometer shows the deflection. And galvanometer shows deflection only if the electric current flows through it and it is connected with the coil. It implies that we can conclude this thing, the current is induced in the coil. Now this particular phenomenon in which the changing magnetic field produces the electric current, that is called electromagnetic induction. That is called electromagnetic induction. So then after he observed this thing, if the magnet is moved towards the coil, galvanometer shows the deflection. If magnet is moved away from the coil, Galvanometer also shows the deflection, but the deflection in the galvanometer that is in opposite direction than the previous one. If south pole is facing to the coil and the magnet is moved, then the same effect is observed. Galvanometer shows the deflection, but that deflection is in the opposite direction than observed during the north pole facing to the coil. Then he observed this thing: if the speed of the moving magnet is increased, then the deflection also increases. Now, if magnet is kept stationary one and the coil is moved towards the magnet or away from the magnet, then the same result is observed. But if both are stationary or both are moving with the same velocity in same direction, then galvanometer is not showing the deflection. So he concluded this thing. The important thing, that is the relative motion between coil and magnet. But then after, he repeated the experiments. Second experiment was like this. In second experiment, he took two coils, C1 and C2. One was connected with galvanometer. Another one was connected with battery. Now, if a steady current is passed through this particular second coil, then no doubt we know this thing, if the current is flowing through the coil, definitely it will produce the magnetic field. So here coil C2 will produce the magnetic field, means now coil C2 itself will behave as a magnet. Now those magnetic field lines are passing through this particular coil C1 also, means some magnetic flux is associated with it. But at present, if both the coils are stationary and the current in the coil C2, that is a steady one, then he observed this thing: galvanometer is not showing the deflection. Now, if either of the coil is moved, means if the relative motion is established between these two coils, then the galvanometer shows the deflection. It implies that in coil number C1, the current is induced, means we can say the EMF is induced in coil C1. Then after, he performed the third experiment. In third experiment, he took two coils C1 and C2, one connected with galvanometer, another one connected with battery and key. And in this particular experiment, he observed this thing: when the key is closed, then galvanometer momentarily shows the deflection and then becomes steady. Now, when the steady current is flowing through coil C2, at that time there is no deflection in the galvanometer. But now if the key is released, then galvanometer shows the deflection momentarily, but in the opposite direction than initial one, and again it becomes a steady one. So finally, with the help of this type of series of experiments, so many experiments were performed, he finally concluded this thing: here motion is not necessary thing. Relative motion is not necessary thing to produce the current in the coil or EMF in the coil. But the important thing, that is the changing flux. And you can change that flux by any means. In third experiment, the flux passing through this coil C1 was changed by changing the current in coil C2. So somehow, if the flux associated with any coil or the closed loop changes, then the EMF is induced in it and the current is constituted in the coil. So with the help of this type of series of experiments, finally he represented this thing. Clear to all of you, or any doubt in this one? Any question? કોઈને કોઈ confusion છે આમાં બેટા?
સર ફર્સ્ટ વાળો થોડું ઉપરથી સમજાવજો કારણ કે ડિસ્કનેક્ટ થઈ ગયો તો મારો એટલે સરખી રીતના નથી ખબર પડી.
હા તો see, suppose coil and magnet are placed as shown in the figure, then we can understand this thing, the magnetic field of the magnet, that is in the surrounding of it. So definitely some magnetic field lines are passing through this coil. So we can say some flux is passing through the coil. But if there is no relative motion between coil and magnet, then the flux associated with this coil, that is steady one. And galvanometer is not showing the deflection. But as soon as the magnet is moved towards the coil or away from the coil, he observed this thing, galvanometer shows the deflection. And if the poles are changed, if south is facing to this one, then if magnet is moved towards the coil, away from the coil, in that case also we will get the deflection in the galvanometer, but the deflection that will be opposite than that obtained during the north pole facing to the coil. So when there is the relative motion between these two, if magnet is steady and coil is moved, then also the same thing is observed. So when there is the relative motion between these two, we get the deflection in the galvanometer. But resultantly, with the help of these three experiments represented here, and more than these three series of experiments were performed, and finally he concluded this thing. The important thing, that is the change in flux. By any means, if the change in flux associated with the coil takes place, then definitely the EMF is induced in it, which constitute the current in the coil. Clear to all of you now? Any doubt, beta?
પડી ગઈ સર ખબર.
Clear? જવા દો આગળ હવે. Okay. Now see, before discussing Faraday's law of electromagnetic induction, we have to take idea about the magnetic flux. Now the concept of magnetic flux, that is exactly like the concept of electric flux, which we studied in chapter number 1. Okay. So electric flux phi E, that we give by equation E dot A. Clear? So electric flux passing through any surface, that is nothing but the total number of electric field lines passing through that surface normal to it. Similarly, magnetic flux passing through any surface, that is the total number of magnetic field lines passing through that surface perpendicular to it. Suppose as shown in the figure here, the magnetic field, that is uniform one, and it is in the direction represented by these red field lines. Now in this particular magnetic field, a surface having surface area A is placed in such a way that the area vector of the surface is making an angle theta with respect to the magnetic field. Then here we can write the magnetic flux passing through this particular surface, that is phi B equal to B dot A, or we can write that is BA cos theta. Okay. Now if the magnetic field is not uniform one, means the intensity of the magnetic field is changing point by point, or we say, suppose we consider the surface which one is not perfectly plane surface, which one is placed in the magnetic field. Then in that particular case, how to find the total flux passing through that particular surface. So here we have to divide this entire surface into so many infinitesimal small surface elements. Suppose one such element, that is the jth element, as shown in the figure, the area vector of that jth surface element, that is delta Aj, and the magnetic field on that particular small element, that is Bj. So we can write the flux passing through that particular small element, that is Bj dot delta Aj. Now, in this way, if entire surface is divided into so many infinitesimal small elements, for each one, if we calculate the flux passing through it, and then after, if we take the summation of all these, we will get the resultant one. We will get resultant one. Clear? દેખાય છે ને બરોબર? So total flux passing through that particular surface, that is sigma j equal to 1 to n b dot delta A. Now if we take limit delta A tends to 0, then the summation can be represented by integration. So magnetic flux passing through any surface, that is nothing but the integration of magnetic field over that particular surface. In the case of electric flux, the equation was also the same type. Integration E dot dA over the surface. Now here unit of magnetic field, that is Tesla. Unit of area, that is meter square. So unit of flux will be Tesla meter square, and that is also known as Weber. That is also known as Weber. Now let's discuss Faraday's law of electromagnetic induction. Now easily one can understand this thing. In previous topic we discussed this thing, when the magnetic flux associated with the coil, by any means, if magnetic flux associated with the coil or passing through the coil changes, then the EMF is induced in it, and which constitute the current. And one more thing we discussed in those experiments, if the speed of the relative motion is increased, then the deflection is more. It implies that more current is constituted. It implies that more EMF is induced. Clear? So with the help of these experimental observations, finally he represented the law of electromagnetic induction, which is known as Faraday's law of electromagnetic induction. And the statement of this law is like this: the magnitude of EMF induced in the coil is equal to the time rate of change of flux associated with that coil. The magnitude of EMF induced in the coil is equal to the time rate of change in flux associated with the coil. So mathematically we can write the EMF induced, that is minus d phi by dt. Clear? Here negative sign give the direction of induced EMF. Later on we will discuss this negative sign in detail with the help of Lenz law. If coil have n number of turns, then simply we can write the EMF induced E, that is minus N d phi by dt. Okay, minus N d phi by dt. Clear to all of you? Any doubt in this one? Then next, that is illustration 6.1. Consider experiment 6.2a. Sorry, consider experiment 6.2. Now question A. What would you do to obtain a large deflection of a galvanometer? Then how would you demonstrate the presence of an induced current in the absence of the galvanometer? Now, if you want large deflection corresponds to large current. So if you want to produce large current, then either you have to increase the rate of change of flux, right? Or you have to increase the speed. Okay, so in these two ways you can increase the current induced, and due to that the deflection that will be more. And second thing, in the absence of galvanometer, how one can detect the presence of current in the second coil or in the coil? So at the place of galvanometer, connect small bulb. So if bulb glow, then we can understand this thing. Yes, the current is flowing through it. Clear to all of you? Simple thing. Then example 6.2. A square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. A uniform magnetic field of 0.1 Tesla is set up across the plane in the northeast direction. The magnetic field is decreased to 0 in 0.7 second at the steady rate. Determine the magnitude of induced EMF and current during this time interval. Very simple thing. Now see, square loop, that is with side 10 centimeter. So side that is 0.1 meter, resistance of it that is 0.5 ohm. The magnetic field that is 0.1 Tesla. And that magnetic field is in northeast direction. And the coil is in east-west plane. It implies that the field and the area vector of the coil both will be at 45 degree. Time interval during which the field is made zero, that is 0.7 second, we have to calculate the magnitude of EMF induced and current I. Now, we have the equation of the flux phi, that is equal to BA cos theta. So, initial flux associated with the coil, that is B1A cos theta, B1.1 area, that is L square, that is 0.1 square cos 45. And final flux, that is B2A cos theta, B2, that is 0. Now, here the magnitude of the EMF induced, that is change in flux upon time interval. So change in flux, that is final minus initial. Initial is this one. Upon time interval, that is 0.7. So here you will get the answer. Now current constituted, that is E by R. Whatever is the answer of E obtained here, substitute it in this equation, you will get the current. Clear to all of you? Then after, example 6.3. A circular coil of radius 10 centimeter, 500 turns and resistance 2 ohm is placed with its plane perpendicular to the horizontal component of Earth's magnetic field. It is rotated about its vertical diameter through 180 in 0.25 seconds. Estimate the magnitude of the EMF and the current induced in the coil. Horizontal component of the Earth's magnetic field at the place is 3 into 10 raised to minus 5 Tesla. Now see here, be careful. Circular coil. શું બેટા?
સર આ ક્વેશ્ચન માં ખબર નથી પડતી શું કહેવા માંગે છે.
હું ફરી એટલે તો રિપીટ કરી રહ્યો છું બેટા.
અચ્છા.
A circular coil of radius 10 centimeter and 500 tons and resistance 2 ohm is placed with its plane perpendicular to the horizontal component of Earth's magnetic field. This is your coil. Okay. This is horizontal magnetic field of Earth, and perpendicular to this one, the coil is placed, means like this. So the area vector is perpendicular to the plane of the coil. So area vector and the field both will be in the same direction. Both will be in the same direction. So initially the theta is 0. Clear? Now here we know this thing, some flux is passing through this coil. Now here it is given to you. It is rotated about its vertical diameter through 180 degree in 0.25 second. હવે આ રીતે કોઇલ છે તો એને આમ કરીને આમ આખી 180 degree એ રોટેશન આપ્યું. ક્લિયર? તો estimate the magnitude of the EMF and the current induced in the coil. તો તમે આને રોટેશન આપ્યું આમ તો obvious છે કે magnetic flux associated with it will change, and if the flux associated with the coil changes, EMF is induced, and we have to calculate that EMF induced. So first of all we have to calculate change in flux. So now see the given data. Radius is 10 centimeters, so 0.1 meter. Total number of turns in the coil 500. Resistance of the coil 2 ohm. Time interval during which this coil is rotated by 180 degree like this, that is 0.25 second. Magnetic field, that is 3 into 10 raised to minus 5 Tesla. What is the EMF and the current that we want to find? Now initially the angle between area vector and the field, that is 0, and then after આમનું આમ આખું ફેરવી નાખીએ તો area vector બી આખો ફરી ગયો, means now field that is in the same direction. So angle between area vector and field in second position of the coil, that is 180 degree. So EMF induced, that is N into delta phi by delta T, that is final flux minus initial, that is delta phi, that is change in flux upon delta T into N. But flux, that is BA cos theta, B and A, that is constant one. So we can write here BA cos theta 2 minus BA cos theta 1, but BA is taken common. So we can write NBA into cos theta 2 minus cos theta 1 upon delta T. Now substitute all the values. Number of turns 500, B 3 into 10 raised to minus 5 given to you. Area, that is pi r square cos 180 cos 0 upon time interval 0.25. And now you will get the answer, the EMF induced. તમારે ધારો કે આવી રીતે ના કરવું હોય અને initial flux NBA cos theta 1, final flux NBA cos theta 2, બે separately ગણી ને પછી તમારે delta 5 by delta T આટલો પોર્શન ડાયરેક્ટ લઈને ગણવું હોય તોય ચાલશે, બરોબર? પણ એ વખતે પછી n અહીંયા બીજી વાર ના મલ્ટીપ્લાય કરતા હો, ફ્લક્સ ગણવામાં n લઈ લીધું છે, અને ના લો તો પછી અહીં મૂકજો, એટલે એવું ડબલ ના કરી નાખતા પાછા. તો I, now the current induced, that is EMF upon resistance. So EMF is obtained here, divided by 2. You will get the answer. Clear? ચલો લખી નાખો. Now see, Lenz law suggests this thing. The polarity of induced EMF tends to produce the current in such a direction which opposes the change in magnetic flux that produced it. Let's try to understand this thing. Okay. See, here, when the magnet is moved towards the coil, then the EMF is induced in the coil. And that in EMF will induce the current in the coil. Now, if current is induced in the coil, means now the current is flowing through the coil. But in previous chapter, we studied this thing. If the current is there, definitely it will produce the magnetic field. It implies that now this induced current, the induced current itself will produce the magnetic field. So if this current flowing through the coil produces the magnetic field, then we can say the coil itself behave as a magnet. If coil behave as a magnet, then second thing, one end of the coil will behave as north pole, another one will behave as south pole. Then the question is this one, which end of the coil will behave as which pole? Now see, let's consider one simple thing. We take one coil connected with galvanometer and resistor as shown in the figure, and against it the magnet is placed in such a way that the north pole of the magnet is facing to the end of the coil. Okay, as shown in the figure. Now suppose the magnet is moved towards the coil, and due to this motion of the magnet, flux associated with the coil changes. Due to that, the EMF is induced in the coil, which constitute the current in the coil. That current will produce the magnetic field, and now the coil itself behave as a magnet. And suppose the end of the coil facing to the north pole of the magnet behave as a south pole. In such a direction, the current is constituted. Clear? And we already discussed this thing. If the current constituted here, that is in clockwise direction, then this end will behave as a south pole, and if it is in anti-clockwise direction, then it will behave as a north pole. So here the end of the coil, which one is facing to the north pole, a north pole, right? So if we observe normal to the plane of the coil, then we can observe this thing, the current constituted at this end, that is in clockwise direction, and due to that, this end of the coil facing to the north pole here, this is the north pole of the magnet, behave as a south. આવું આપણે consider કર્યું છે, આપણે આવું ધાર્યું છે, વિચાર્યું છે. But if This is the fact. Then what happens? See, now if this end becomes south, then it will attract north. Means it will exert the attractive force on north pole. So during the motion, if the force acts on it, then its momentum increases, means speed increases. Means we can say the motion that will be accelerated one. So now if speed increases, then the flux associated with the coil changes rapidly. Means the rate of change of flux increases. Due to that, more EMF will be induced. If more EMF is induced, then more current will be constituted. If more current is constituted, then more magnetic field will be produced by that current carrying coil. It implies that the end of the coil, which behave as a south pole, that will becomes more stronger. If it becomes more stronger, then the attractive force on the north pole will increase. It implies that magnet will move towards the coil with continuously increasing acceleration. It implies that once just you give slight motion to the magnet, and then after magnet will start running towards the coil. Now if here we connect this resistance, then as per I square RT, here we will get the heat energy. Now without spending energy, you are getting heat energy here. A violation of law of conservation of energy. કોઈ દિવસ આવું ના possible થાય. Right? એક એનર્જી જનરેટ થાય તો સામે બીજી એનર્જીનો લોસ થતો જ હોય. રાઈટ? એનો મતલબ શું થયો કે આપણું જે એઝમ્પશન છે ને એ રોંગ છે. આ સાઉથ ના બને તો પછી શું બને? નોર્થ બને. બીજું ક્યાં કોઈ ઓપ્શન છે જ આપણી પાસે. Right? It implies that if the magnet of the north pole is facing to the end of the coil and moving towards it, then the magnetic flux changing associated with the coil will produce the EMF in such a direction so that the current induced by it will be in such a direction so that the magnetic field produced by that particular current will exert the repulsive force on this magnet. So now again the statement, the polarity of the induced EMF tends to produce the current in such a direction which opposes the change in magnetic flux that produced it. એટલે કે EMF જેના લીધે કરીને જનરેટ થયું છે, પ્રોડ્યુસ થયું છે, એ કોઝ જે છે, એ જે રીઝન છે, એનો જ ઓપોઝ કરે એવી રીતે એ કરંટ કન્સ્ટિટ્યુટ કરે છે. પડી સમજ બધાયને? ક્લિયર એકદમ? Now you can easily understand the presence of this negative sign in the Faraday's law. This negative sign that is due to Lenz law. Due to Lenz law. So this negative sign indicates this thing. This EMF induced will produce the current in such a direction so that it opposes the cause of its production. So negative sign Lenz law ના લીધે કરીને આવેલી છે ત્યાં આગળ. ચલો. Now example 6.4. Okay. Figure 6.7 shows planar loops of different shapes moving out of or into a region of a magnetic field which is directed normal to the plane of the loop away from the reader. Determine the direction of induced current in each loop using Lenz law. Now see, suppose first we think about this rectangular loop. Now this particular loop is going inside the magnetic field. Here magnetic field that is perpendicular to the plane of paper and going inside. Okay. Now if this particular coil is going inside, then the flux will be increasing one because B is constant one. But the area of the loop through which the field lines are passing, that area is continuously increasing. So flux associated with this one increases. Now the current will be constituted in such a direction so that it opposes this change. હવે આ ચેન્જ નો ઓપોઝ કરવો હોય તો ફ્લક્સ વધી રહ્યું છે, તો ઓપોઝ કરવો એનો મતલબ કે ફ્લક્સ ઘટે એવી રીતે કરંટ કન્સ્ટિટ્યુટ થાય. તો હવે આગળ ઉપર આપણે જોઈ ગયા કે the current constituted in the coil itself will produce the magnetic field. So here logically now we can understand if the direction of the current is such that the magnetic field produced by that current is in the opposite direction of our original magnetic field, then the net field will decrease. And here due to motion of the coil, the flux is increasing one. So this current constituted will produce the magnetic field in such a direction so that the net field decreases. So it will try to decrease the flux. એટલે અહીંયા જુઓ B, C, D, A, B ડાયરેક્શનમાં કરંટ કન્સ્ટિટ્યુટ થાય. તો કરંટની ડાયરેક્શનમાં તમે ફિંગર મૂકી દો આવી રીતે. આગળ ઉપર આપણે ભણ્યા કરંટની ડાયરેક્શનમાં હું ફિંગર મૂકું તો થંબ મારી બાજુ આવશે અને આપણું ઓરિજિનલ ફિલ્ડ જે છે મારાથી દૂર જતું છે, પ્લેન ઓફ પેપર ગોઈંગ ઇનસાઇડ છે. તો આ જે કરંટ કન્સ્ટિટ્યુટ થશે that will produce the magnetic field in outward direction. તો બંનેનું વેક્ટર સમેશન કરીએ તો નેટ ડિક્રીઝ થાય. ક્લિયર? તો ફર્સ્ટ કેસની અંદર the direction of the current that is BCDAB. Now second case, in that the coil is moving outward. So when coil is moving outward, the area of the coil through which the field is passing, that is continuously decreasing one. So flux associated with it is decreasing one. So now the induced EMF will constitute the current in such a direction so that the produced magnetic field will try to increase the flux. તો એ કેસમાં જે external field છે એની પોતાની જ ડાયરેક્શનની અંદર ફિલ્ડ આવે એવી રીતે કરંટ કન્સ્ટિટ્યુટ થાય. તો જો આમ થઈને આમ બતાવું કરંટ તો થંબ તમારી બાજુ આવે તો એક્ઝિસ્ટિંગ ફિલ્ડ તમારી બાજુ છે. તો બંને ફિલ્ડનું સમેશન થઈ અને ફિલ્ડ ઇન્ક્રીઝ થશે. તો પછી ફ્લક્સ આ કરંટ જે છે એ ફ્લક્સને ઇન્ક્રીઝ કરવા ટ્રાય કરશે અને ડ્યુ ટુ મોશન ઓફ કોઇલ ફ્લક્સ ડિક્રીઝ થઈ રહ્યું છે એટલે એનો ઓપોઝ કરે. The same concept, this third ring is going outward, so flux associated with is decreasing one. So current constituted will try to increase the flux because it will oppose the change. So again here the current is in clockwise direction, so the field produced by it that is going inside and that is in the direction of our external field. The field નું સમેશન થશે એટલે કે જે ફ્લક્સ ડિક્રીઝ થઈ રહ્યું છે એને એ ઇન્ક્રીઝ કરવાનો ટ્રાય કરશે. Clear to all of you, or any doubt in this one, or any question? Then after, example 6.5. A closed loop is held stationary in the magnetic field between the north and south pole of two permanent magnets held fixed. Can we hope to generate the current in the loop by using very strong magnet? If you take weak magnet or strong magnet, but if the magnet and coil both are fixed one, then flux will not be changed. And if flux associated with the coil is not changing, you will never get the EMF. Then B, a closed loop moves normal to the constant electric field between the plates of the large capacitor. Is a current induced in the loop when it is wholly inside the region between the capacitor plates? When it is partially outside the plates of the capacitor, the electric field is normal to the plane of the loop. Simple answer, no, because EMF can be generated with the help of varying magnetic field, not with the help of electric field. A rectangular loop and a circular loop are moving out of the uniform magnetic field region to a field-free region with a constant velocity v. In which loop do you expect the induced EMF to be constant during the passage out of the field region? The field is normal to the loop. તો ફિગર જુઓ ટેક્સ્ટની અંદર આપણને તરત ખ્યાલ આવશે કે when both the loops are moving out of the field, then the rate of change of area for the rectangular loop, that will be constant, but for the circular one, that will not be constant. કારણ કે આ રીતે circular loop છે, બરોબર છે. હવે માનો કે આપણે ફિલ્ડ જે છે, હું ધારો કે અત્યારે આ રીતે બતાવું. હવે આમાંથી જો આમ બહાર આવતું હોય તો પહેલા આટલો એરિયા બહાર આવ્યો, પછી એરિયા મોટો થઈ ગયો, પાછો એરિયા ઘટી ગયો. જ્યારે રેક્ટેન્ગ્યુલર હોય આવી રીતે તો પછી જે એરિયા બહાર આવતો હશે એ કોન્સ્ટન્ટ આવશે, rate of change of area. Clear? Then after, predict the polarity of the capacitor in the situation described by figure 6.9. તો નોર્થ પોલની અગેન્સ્ટની અંદર આપણે ઇમેજિન કરીએ કે આ બાજુ નોર્થ છે ને અહીંયા કોઇલ છે, right? Then upper plate, that A will be positive. So if A is positive, B is negative. So positive to negative like this. So if anti-clockwise current is constituted, then north against it, north will be generated as per Lenz law. So upper plate A will be positive, lower will be negative. Then after, motional EMF. ચલો ક્લિયર અહીં સુધી બધાને? કોઈને કી ડાઉટ છે, કંઈ પૂછવું છે? ચાલો, motional EMF. Motional EMF means when the change in flux takes place due to any type of relative motion, then the EMF induced, that is called motional EMF. Now suppose, as shown in the figure, we consider one U-shaped frame as shown in the figure, and now the magnetic field, that is uniform one, perpendicular to the plane of paper and going inside. Now take a conducting wire PQ, which one is placed on the arms of the U-shaped frame, and now it is moved with velocity v in the direction as shown in the figure. Now suppose this part SR of the U-shaped frame that is equal to length L, and initially the conducting wire PQ is at distance x from the SR side. Now see here, as soon as we place the conducting wire here on the arms of the frame, then a rectangular loop is formed, PQRS. This rectangular frame is this one. Now if PQ is moving with velocity v, then the area of this particular loop PQRS that will change, and if area is changing one, B is constant one, then the flux passing through that particular closed loop that is continuously changing one, and due to that the EMF will be induced in this one. Now see here, when the conducting rod is at PQ, the flux associated with the PQRS, this rectangular loop, that is B into area of the loop. So area of the loop, this side is L, this one is X, so BLX. Now if PQ is moving with velocity v, L remains constant, but this X is continuously changing one. So EMF induced, that is minus d phi by dt, and that is minus d by dt of phi, that is BLX, B and L constant, so minus dx by dt, and minus dx by dt, that is V. Okay. Now here the EMF induced in this particular rectangular loop will produce the current in such a direction so that it opposes the cause of its production. And here the cause of the production, that is the velocity of PQ. So this velocity will be opposed, and due to that the velocity will decrease. So minus d by dx by dt, that is taken as V. Now in another way also we can derive this particular equation of the motional EMF, which is BVL. Now see, if this conductor PQ is moving with velocity v, it implies that all the charges residing in that conductor are also moving with the same velocity v. With the same velocity v. Now we know this thing, when any charge Q is moving with velocity v in the magnetic field B perpendicular to it, then the force acts on it, that is QVB sin theta. Sin theta, that is 1. So that is QVB. Now, therefore, work done to move charge Q from P to Q, because under the effect of this force is perpendicular to V and B. And as per equation F equal to Q into V cross B, if you find out the direction, then the force acts on charge Q that will be in the direction from P to Q. P to Q, in that direction the force will act. So work done to move the charge Q from P end of the conductor to the Q end, that is W equal to force into displacement. So force, that is QVB, and when the charge is moved from P to Q, the displacement, that is equal to L. A portion L લીધો છે આપણે. Now EMF induced, that is work done per unit charge. આપણે આગળ જે બેટરી ને સેલ્સ ભણ્યા હતા એની અંદર આ વસ્તુ આપણે ડિસ્કસ કરી હતી, right? So EMF, that is nothing but the work done per unit charge. So take this charge on left hand side. So we will get work done per unit charge. That is the EMF E equal to QVB into L upon Q. QQ will be cancelled and you will get E equal to BVL. So this one is the equation for motional EMF. Clear to all of you? चलो आमा कोईने की डाउट करो. Okay. Then after in text one more equation is given to you, that is the equation of Lorentz force. We know this thing, the Lorentz force F, that is Q into E plus V cross B. Suppose the conductor is stationary. If conductor is stationary, then the velocity of the charge, that will be equal to 0. And if velocity of the charge is 0, then magnetic force on the charge will be 0. So the only force will be Q into E. Q into E. So here the force acting, that is due to electric field, but this electric field, that is due to that EMF produced. Okay, and here we consider the magnetic field, that is changing one. So changing magnetic field produces EMF, that we say. So we can say this thing, the changing magnetic field produces the electric field also. Clear?